Today, on How It's Made. Footballs. We hike through a factory that makes pigskins from cow skin. Electric guitar amplifiers, giving rockers a needed boost. Marbles. Ever lose yours trying to figure out how they get those color swirls inside? And airplane propellers. Time flies on this production line. In 1869, players in the first football game used a round ball like in soccer. It was tough to carry and awkward to throw, so they changed it to look more like a watermelon. The current shape enables a better grip and passing on an arc that's unique to football. A lot of people handle a football before it ever gets to the field. They start with cowhide. Footballs are traditionally made of this leather because it wears well over time. With a die, a worker cuts out the 4 sections that make up the ball's skin. A stamping machine then brands the skin with the company logo. They may put other markings elsewhere on the ball, depending on the design of the model they're making. Each of the sections goes into a machine that trims the piece's combined weight down to spec. To strengthen the skin, a seamstress sews cotton and vinyl linings onto all 4 sections. Then she places them in a die that positions them for another set of markings. These 4 white lines will form 2 stripes when the sections come together. This is purely aesthetic and varies according to the football model. Now it's time to sew the top sections together and then the bottom ones to each other. Exactly how many stitches this takes is part of this company's closely guarded playbook. This press makes a hole in one of the top sections for the air valve. They make 8 holes in the top sections for laces that'll hold the skin tightly around an inflated bag called a bladder. To join the ball's top and bottom sections, the seamstress first cups them and then joins the edges together. She sews the leather inside out to make the stitches less visible. Later, workers will turn the skin right side out by reaching through the opening between the lace holes. This is also where they'll insert the bladder. It's important to flatten the 4 seams. To do this, a worker places each one on a wheel as a roller passes over the top. This keeps the ball from being bumpy when they stretch the skin over the bladder. A 15-second steam softens the leather and makes it easier to manipulate. A concave press flattens the seams at the tips. This will also keep the ball smooth when they inflate it. Time to turn the skin right side out. A worker places it on a metal bar, then reaching through the opening between the lace holes, he grabs the other side of the skin and pulls it through. Then he runs the bar along the inside to reshape the skin. The bladder's made of polyurethane, a type of plastic, with a vinyl patch reinforcing the lacing area. After squeezing the bladder inside the skin, a worker snips off the end of the air valve to keep it out of the way. Then she inflates the bladder a bit to make it rigid enough for lacing. After steadying the ball with clamps, she uses an awl to thread the lace through the holes. That's right, just one vinyl lace measuring 1.2 meters. It worms through both sides and then down the center and through all the holes once again. The lacing's spaced a little more than a centimeter apart, wide enough to comfortably grip for that magic pass you've got in mind. Next, workers temporarily overinflate the balls. Steel molds surround them to ensure they assume the correct shape. After 90 seconds, the extra air seeps out. Finally, the factory inspects the balls to ensure they're up to standard. Fully inflated, A ball must weigh no more than 425 grams. It should measure 55 centimeters through the middle and 71 centimeters around both ends. After a 5-day scrimmage through the factory, these balls are ready for kickoff. You have to plug an electric guitar into an amplifier if you want it to be more than barely audible. A guitar amplifier is typically a boxed unit containing an amp to boost the electronic signal and a loudspeaker. Some amplifiers use state-of-the-art silicon chip circuitry, while others use traditional vacuum tubes. The amp's electronics are housed inside a metal chassis. This model's chassis is made from a sheet of steel that's less than 1 millimeter thick. A computer-guided machine called a turret punch cuts the contour and pierces a series of holes and slots for the controls. A worker then uses a computer-guided bender to shape the chassis cutout. Elsewhere in the factory, the amp circuit board takes shape. It'll go inside the chassis. A computer-guided drill makes tiny holes in a laminate board that's coated with copper. The holes are for the board's various electronic components. An automated silkscreen printer now applies a diagram of the electrical circuitry in ammonia-resistant ink. Then the board goes into a machine called an etcher, which uses ammonia to dissolve the copper coating. Copper shielded by the ink diagram stays intact. The machine then rinses the board with sodium hydroxide to dissolve the ink, leaving behind just the circuitry diagram in copper. This copper configuration will conduct electricity to the circuit board components. Automated machines insert the smaller components. Here's what that looks like in slow motion and at actual speed. As a worker provides counter-pressure, a machine folds over the leads of some larger components to secure them to the board until they're soldered. Workers then install large, irregular parts by hand. Among them, the sockets that hold the tubes which power the amp. The ribbon connectors that join different areas of the circuit board. And the wires that connect external components to the board. The factory permanently affixes everything in one shot, using a process called wave soldering. The circuit board runs through a bath of molten tin and lead. In just a couple of seconds, the liquefied metal hardens, bonding the components securely. Back to that steel chassis we saw them bend into shape earlier. Since then, they've painted it black. With a silkscreen printer, they apply the control markings, logos, and other information. They begin the final assembly. First, they screw the circuit board into the chassis. Then they plug the preamp tube into the appropriate socket on the board. This tube boosts the electrical signal coming from the guitar and feeds it to the output tubes, which up the voltage level, making the signal stronger and louder. After installing control knobs and covering the bottom of the chassis, workers insert and clamp the output tubes, the number of which usually varies according to how many watts of power the amp is designed to produce. The chassis housing the electronics goes into a box. This factory builds its boxes from high-grade Baltic birch plywood, but other companies often use domestic plywood, MDF, or even plastic. After covering the box in leatherette and adding corner reinforcements, they install the two remaining components, the spring reverb speaker. As the guitar's electrical signal runs through the amp, part of the electrical signal diverts to one end of the spring, vibrating it. The spring's other end picks up this vibration and sends it back through the amp as a delayed signal. That reverberation combines with the original signal to produce a bigger sound. People have been playing with small balls of stone, clay, or marble since ancient Egyptian and Roman times. Today's marbles are actually made of glass and used for industrial tasks as well as games. Glass is not only inexpensive and durable, but also quite beautiful. To make marbles, this company melts recycled glass with marbles made earlier but rejected for being the wrong size. All this goes into a kiln heated to 1,204 degrees Celsius. After 16 hours, they open a door at the bottom of the kiln and the molten glass flows out. A shearing device cuts the stream every half a second, forming segments called slugs that become marbles. To make different sized marbles, they adjust the device to cut at shorter or longer intervals. The slugs slide down chutes, landing between grooves on spinning cast iron rolls. The spinning keeps the slugs from sticking. They'll need 72 hours to cool completely, but their final appearance is already set. That was determined back in the kiln when the airflow drove the heat to melt the glass and mix the colors. These channels separate the good from the bad. Openings along the way weed out the marbles that are too big or too small and collect the ones that are just right. More intricate marbles are handmade. This craftsman first preheats some clear glass in a small oven. Then he breaks off a piece of colored glass. After the clear glass has melted in the furnace overnight, he gathers some on a steel rod, then picks up a chunk of preheated colored glass with it. He forms a knob and works the mass into a long string that's up to 5 meters long and thin as a noodle. He'll use them in various colors to decorate the clear glass cores of the marbles. He gathers a clump of melted clear glass on the rod and shapes it with wet newspaper, which won't stick to hot glass. After shaping the end, he rolls the clump on several preheated colored glass strings. Then it's back in the furnace. He repeats these steps up to 3 times and rolls the clump on a metal table to even out the surface between each trip to the furnace. Then he adds a layer of clear glass on top. With another tool now, he stretches the clump to about 1/2 meter long. He'll use this to make several cores. To make the second layer of the core, he rolls a 5 centimeter long segment onto colored glass slivers called ribbons. After rolling them in the furnace to melt them, he flattens the ribbons with pliers and snips off the excess at the ends. He wraps the core and the ribbons in a layer of clear glass, then hand shapes it. Now he rolls the core on more glass strings. Then it's back in the furnace to meld them. He adds one more clear glass layer, and the inside is finished. That's a total of 6 layers for this marble. Other models have fewer or more. The craftsman shapes the glass with several metal and wooden tools. He measures the diameter with metal calipers and gradually sculpts a sphere. He'll make up to 5 marbles from this segment, ranging up to the size of a golf ball. After scoring the glass with a knife, he places it in the open end of a pipe to hold it. Then he gently taps the rod, which breaks the glass, and releases the sphere. He melts away the bump left at the spot where the glass broke. Next, the marble goes into an oven at 530 degrees Celsius. The oven slowly cools overnight to strengthen the glass. Clearly a cut above, this eye-catching, handcrafted marble is already an objet d'art. An airplane propeller usually has 2, 3, or 4 blades, the angles of which the pilot can adjust in response to airspeed and flight conditions. A propeller's main parts are made of aluminum because it's critical to keep it as lightweight as possible. The blades and hub are made of aerospace-grade aluminum that resists corrosion and metal fatigue. The propeller's blades attach to a hub. This piece of aluminum is on its way to becoming that hub. Like the starting pieces for all parts, it was forged beforehand into a rough version of the final shape. This sophisticated, computer-guided mill now machines the piece. 40 minutes later, the hub is finished and ready for assembly to the engine. This roughly shaped piece is about to become one of the propeller's blades. A computer-guided lathe machines it to the final shape. Liquid lubricant washes away the metal shavings and cools the friction-generated heat. The lathe first forms the shank, the end of the blade that fits into the hub. The next milling machine cuts the blade's shape. Now the finishing steps, done manually because they require a keen eye. Workers use a rotary sander, then a belt sander to grind away the marks the machining process left behind. They buff the metal with a polishing wheel. Then clean the blades by dipping them in a strong detergent. This acidic solution eats away any dirt, oil, or grease on the surface of the metal. After that, they dip the blades in a bath of water and chromic acid. This seals the pores in the metal, fending off corrosion. The factory tests all critical parts for surface defects by dipping them in a fluorescent solution that leaches into any imperfections. After rinsing, an inspection under black light. A blue glow means the parts are A-OK. Any imperfections show up as bright fluorescent green. The defective part is either repaired or rejected from the production line. Blades that get the blue light move on to the paint shop. A coat of black on the backside to prevent sun reflection into the pilot's eyes, and stripes for safety to make the spinning blades visible. Next comes a de-icing boot, a rubber-encased electric heating element that prevents ice buildup. The rubber is highly durable, yet flexible enough to mold to the curve of the blade. Next, they lubricate a part of the blade shank with grease, then install a strong steel ball bearing system. This will hold the blade securely in the hub, yet still enable it to pivot to change its angle. The shanks of the 3 blades fit right into the steel part called the fork. It keeps all the blades at the same angle. Now for what's called the pitch change rod. The term pitch refers to the angle of the blades. Engine oil will exert hydraulic pressure on a piston that moves the pitch rod, which advances the fork, rotating the blades to the required angle. After removing the pitch change rod temporarily, they apply sealant to the top half of the hub, and place it over the bottom half that contains the ball bearing set. A rubber O-ring seal, then a sturdy spring to provide the required counter pressure. Workers thread and torque the piston and pitch change rod, now attached to each other, to the fork. Another rubber O-ring, this one to prevent leaks out the top of this cylinder that'll contain the engine oil. They use a special tool to tightly torque the cylinder down against the hub. Assembly is now complete, and the propeller is ready to go for a spin.